Good morning, Calculus BC class today. So it's Mr. Chen. So today I would like to talk about the alternating series tests. So this one is for 9.5. So for the alternating series test, so let a sub n, the sequence, it's greater than 0. The alternating series, sigma negative 1 to the power of n times a sub n. So with n equals 1 to infinity, or sigma n equals 1 to infinity, negative 1 to the power of n plus 1 times a sub n. Converge. So either one of those, okay, so the series converges if the following two conditions are met. So we do have two different criteria that we need to verify in order to make sure that the alternating series converges. Okay, so one of the conditions is that a sub n plus 1, it's less than or equal to a sub n for all the value of n, while where n is the natural number. And the other condition is that limit of a sub n as n approaches infinity, it's always 0. So it doesn't matter which condition that you verified it first, as long as we satisfy those two conditions. So that means the alternating series always converges. Now what happens when one of the conditions fail? If one of those conditions fail, then you stop, and then you can just conclude that the alternating series diverges. Okay, so now let's find out the following. Determine the convergence or divergence of the series, negative 1 to the power of n plus 1 over 1 over n. So one thing that we want to verify first is to take out a sub n. So we do know that a sub n is 1 over n without looking at the negative 1 to the power of n plus 1, the indicator for alternating the series. So one thing that we want to verify is that the limit as n approaches infinity. So let's find out what happened with that 1 over n. So 1 over infinity, obviously it's 0, so it satisfies the second condition. And now another thing that we want to verify here is that a sub n plus 1, a sub n plus 1. So what we found here, it's considered 1 over n plus 1. So compare and contrast. So 1 over n plus 1, it's actually less than or equal to 1 over n. Well, I'll just say that it's less than. Okay, so just less than. So basically this one is satisfied all those conditions. So once we satisfied all those two conditions, so you can just say that the series negative 1 to the power of n plus 1 over 1 over n converges. Okay, so now let's take a look at that. The other example, determine convergence or divergence of the series. So first thing that you want to find out is that a sub n. So we do know that it's considered n plus 1 over n. Another thing that you want to verify here is that the limit n goes to infinity of that a sub n. So we do know that it's n plus 1 over n. And you may be noticing here, so the limit for this one, if you take out the greatest common factor n, so we got 1 plus 1 over n. Denominator, just leave it as the way it is. So n, just cancel that out. And again, n goes to infinity. So what we found here, it's 1 plus 1 over infinity. So this one is just considered 1. Definitely you can use the L'Hopital's rule for this one because that's an indeterminate form. So according to the satisfying condition here, so for condition number 2, so the limit of a sub n as n approaches infinity must be 0. But according to what we found here, it's 1. So therefore, the series automatically diverges. So again, one of those conditions fail, so that means the entire series diverges. And here's another one. So this one is also for the alternating series test. It's called the Absolute Convergence Theorem. So if the series of absolute value of a sub n with n equals 1 to infinity converges, then the series a sub n from n equals 1 to infinity also converges. Okay, so this one is the conditional statement, and also if you just put it here, so this one is considered the theorem. So definition, if the series a sub n from n equals 1 to infinity, it's blank. Well, this one, let's put in this. It's conditionally converging if the series converges, but the absolute value of the series, absolute value of a sub n, diverges. Okay, so gotta be careful. Absolute value of the series here diverges, but the series itself converges. So therefore, the series itself is saying that it's conditionally convergent. And what about this one? This one is just like going back to what we found for the absolute convergent theorem. So if the series a sub n is convergent, if absolute value of a sub n, the series converges. Okay, so got to be very careful with that. There's another condition here as well. The third condition would be that both of those series diverge. Okay, so the absolute value of the series diverge and the series itself also diverge. So let me just put it right here. So condition number 3, both of the series itself and absolute value of this a sub n diverge. Okay, so that would be the third condition. So let's go back to the first example and determine if it's conditionally convergent or absolutely convergent. Okay, so now going back to the first example here. So we got -1 quantity to the power of n plus 1 times 1 over n. Okay, so going back to the first one. So first thing that you want to verify is the absolute value. The absolute convergent. So let's just start it with sigma n equals 1 to infinity. So absolute value of -1 quantity to the power of n plus 1 and 1 over n. And you may notice that absolute value, that means it makes everything positive. So what's left here, it's only 1 over n. So just absolute value of 1 over n. So got to be very careful with this one here. So this one, if that's absolute value of 1 over n, so this one basically give you the harmonic series. So for doing that, the harmonic series for the previous video, we're saying that it's always divergence. Okay, so for the absolute value of the series, so this one definitely diverge. Because it's a harmonic series. And also we proved that with the integral test for the previous video. And now another thing that we want to verify is that the series itself. So this one, it's an alternating series, and for the previous one we did it already. If that's an alternating series, so it converges. Okay, so this one we just did it earlier, so this one converges. So going back to the example, so this one definitely it's considered conditionally converged. So therefore the series is conditionally convergent. Okay, so now let's see what else that we have for this one. So the other one is that the okay, let me just put it right here. So sigma with n equals 1 to infinity of the sequence -1 to the power of n over square root of n. So first thing that you want to do, you want to find out whether that's its absolute value, it's absolute convergent. If this one is absolutely convergent, so that means the series itself also converges. Okay, so let's verify that. So absolute value of -1 to the power of n over square root of n. So again, -1 to the power of n, that's just an indicator for alternating the sign. So it's always guaranteed that with the absolute value, so this one's going to be positive. So what we got here is absolute value of 1 over root n. And this one, just rewrite it. So it looks like it's going to be the p series. Always rewrite it. So absolute value of 1 over n to the power of 1/2. And you may notice that, so P it's 1/2, which is less than 1. So that means the series sigma n equals 1 to infinity, absolute value of -1 to the power of n over root n diverges. Because that's the P series. And now let's just verify the series itself. So we do know that it's an alternating series. So take out that a sub n, so we got 1 over n to the power of 1/2. So using that, the alternating series test, so first thing that you want to do, verify the limit, n goes to infinity. So 1 over infinity, well, let me just rewrite it. So limit as n approaches infinity, so 1 over n to the power of 1/2, so 1 over infinity to the power of 1/2. So we do have 1 over infinity, which is 0, so it satisfies one of the conditions. And let's find out that a sub n plus 1, because you want to compare that a sub n. So a sub n plus 1 is considered 1 over n plus 1 to the power of 1/2. Okay, so 1 over n plus 1 to the power of 1/2, compare the quantity in the denominator. Well, obviously this number is going to be bigger than this, but it's in the denominator. If the denominator is getting bigger, so the entire quantity is getting smaller. So therefore a sub n plus 1, it's less than a sub n. So 1 over n plus 1, quantity to the power of 1/2, it's less than 1 over n to the power of 1/2. So let's say that if you plug in n equals 1, so this one is 1 over root 2. But on the other side here, a sub n, it's just 1 over 1, which is 1. So obviously 1 is greater than 1 over root 2. So therefore, by using the alternating series, so the series itself converges. So therefore, -1 to the power of n over root n, the series itself. So this one is considered conditionally convergent, or conditionally converges. Alright, so that's it. So thank you for watching the video today. If you guys do have any comments, any questions, so feel free to put into the comment YouTube channel bar. So I'm more than happy to reply that. So I'll see you guys next time. Take care. Bye.